Alright, welcome to lesson 6. In this lesson we're going to add an additional layer of cloth below our bag so it catches the falling sand and will make it breakable as well, so we see more cloth tearing apart. So first let's create our grid. Make it 1.5 by 1.5 and let's make it 0.6 in the y-axis. And let's remesh our grid like we did with the bag, but this time I want our wireframe to be denser at the middle of the grid, so we have more points, and as we go out to the edges I want fewer and fewer points, so that when the sand tears our grid apart we'll have more cloth fragments in the center than out in the edges. So to do this, let's first drop down a remesh node, and let's change the way the node computes the edge length from uniform to adaptive. So we get these control attributes, and what we want to use is this mesh size attribute called target mesh size. And as always, when we have an attribute that we need to manipulate, we always go to and attribute VOP. So let's drop down an attribute VOP. And this time, instead of using noise, we want a controlled gradient from the center going to the edges. And there's a lot of different ways to do this. The easiest thing for me in this case is to isolate a point from the center of the grid and compute the distance from that center point to the rest of the points in the grid. And that will result in a circular gradient automatically. So let's drop down a blast node. And let's select a point in the center, or near the center of a grid, let's say this one. Delete non-selected, so we isolate our point, and let's connect our point to the second input of our VOP, and let's dive inside. So here we have the position attribute of the whole grid, and to get the position of the second point, we need an import point attribute node, and let's connect our file with the op input 2, since our point data is coming from the second input. And to compute the distance, we'll drop down a distance node, and let's connect our positions. And to have more control over our gradient, we'll use a fit range node and bind export this whole thing as our target mesh size. Let's promote our fit range parameters to the outside, and let's create a visualizer for our target mesh size, and voila. Now we have a gradient that we can use to set our minimum and maximum mesh sizes. So let's say our smallest mesh size is going to be 0.015 and our largest will be 2. And let's widen the area where our small mesh is, so we need to see this blue area getting larger. So let's say 0.75. And to make the transition between the small and large meshes more smooth than this, we need to take our maximum value up. So let's say 4. So we have a smooth transition between our mesh sizes. So let's see if this worked. Let's get rid of our visualizers and see our wireframes, and let's see our remesh node. And we now have different amounts of points going from our center to our edges. And let's take our gradation down as well, so we have more wireframes overall. So let's say 0.08 instead of 0.25. And let's make our relative density 1 instead of 2, and maybe take our iterations down to 1 as well. So I think this is fine for now. So we're ready to convert this into a cloth object now. So first, let's drop down an edge fracture node to make it breakable. We can actually copy the one that we already have and just mess around with its parameters. Let's visualize our pieces. And I want more pieces than this for this sheet. So let's say our initial pieces will be 150. And let's dive down and mess with our mountain options as well. And we need something to hold our cloth object in place, so let's create 4 wires that hold it from the angles. So what we're going to do is isolate these 4 points, and we'll scale our grid up, isolate the same points from the bigger grid, and connect them together to create a wire. And to do this, we first need to assign an ID attribute to our points, so Houdini knows which points to actually connect. So let's drop down an attribute triangle. and let's type I at id, so it's an integer attribute, equals pt num. So now each point will have its own id attribute. And let's isolate our 4 points. So drop down a blast node and select the outer 4 points. Delete non-selected, so we isolate them. And let's copy this thing over here. Let's actually copy our group and paste relative references. So if we ever decide to choose other points than these, the other blast will get updated automatically. And let's drop down a transform node before this angle right here. And let's scale up our grid by 1.5 in the X and 1.5 in the Z. And just to be sure everything is correct, let's translate our pivot in the y-axis by 0.6, so we're sure it's in the center of our grid. Let's merge these two nodes together, and to connect them we will need an add node. Let's go to our polygons tab, connect them by group, and add points by attribute, and our attribute in this case is the ID attribute. Alright, now we have our 4 wires, and since we don't need our ID anymore, it can actually cause problems since we have multiple IDs that are the same, so our solver won't like that. Let's get rid of it, so drop down an attribute delete and get rid of our ID attribute. So we only have 2 points per wire right now, and we will need more points than this. So let's drop down a resample node. Let's take down our length to 0.05, so we have more points than this. And I think that's enough. This way our wire will now bend properly, and you can think of this as a way to increase your wire's resolution. And to have a completely clean setup, let's fuse our points together, so in case we have points that are on top of each other, they get deleted and don't cause any problems in the solver. So let's drop down a fuse node. And to differentiate our wires from our cloth sheet, let's make a group for them. Let's call it wires and change our group type from primitives to points since we don't have any primitives yet. And now we can actually merge our wires together with a cloth. So let's drop down a vellum, configure cloth. First thing, let's change our group type to points, and in this group right here, let's type asterisk, circumflex, wires. So now the node understands that we want everything to be treated as a cloth object except for our wires group. And let's set our mass to 0.2 like our bag, and get rid of our compression stiffness. Do the same thing with our vellum weld, so we can glue together our fractured edges. Also in the group, let's say point group, asterisk, circumflex, wires. And let's turn on our threshold, and let's leave it like this right now, and we will actually come back to this again in a second. Let's first drop down another Weld Constraints node. Set the type to string, and we will only need a wires group this time. Let's actually set the mass really high so it doesn't get affected by the cloth getting hit by our sand. So let's take this up to 5, and let's actually set our thickness manually, so later when we change this into polywire it doesn't look weird. So let's set uniform our thickness, visualize it, and maybe increase this to 0.02. I think this is enough to manipulate later. And let's choose pinpoints. Let's choose the outermost point of every wire to hold our entire thing together. And now we're ready to import this into our DOP. But before doing this, let's get back to our break threshold real quick. What I want in this case is lower threshold in the center and a high threshold at the edges, so the center will be more easy to tear apart. And since we've already done the same thing with our remesh, I'm going to duplicate our VOP, put it before our edge fracture, and let's change our bind export to break threshold scale. So we'll use this attribute as a multiplier for a brick threshold. So let's set our minimum value to 1, so it multiplies by whatever value we specify in the brick threshold scale in the vellum weld constraints. And let's take the maximum value all the way up to 5, so it really isn't easy to break as the middle parts. Let's visualize this real quick. And let's take our minimum value to 0.6 and our maximum value to, let's say, 1.5. Okay, let's now go to our vellum weld constraints, scale this by attribute, and it will use our brick threshold scale that we made and change the type to stretch ratio just as we did with the bag, and maybe take this up to 0.2 so it's more easily breakable than our bag, which is now sitting at 0.25. And let's create our nulls now. So one for the geometry and one for the constraints. And since we've named this cloth geo, I'm going to be very creative with the naming in this one. I'm going to name this cloth 2 geo and cloth 2 con. Alright. So let's actually import this into our DOP now. I'm going to bypass our class object, duplicate this, name it cloth 2, and change our subpath to cloth 2 geo and cloth 2 con. And we will need to move our ground plane down as well, because if the grains come down and hit our cloth right now, it will hit the ground since they are so close together. So let's take this down to -1 in the y-axis, so it has more room to move freely. And let's actually make a flipbook and see what this will get us right now. Alright, this is looking good right now. I like the way the cloth fragments look, and I like this violent rebound that the wires make the bag give our sand. So let's get our bag back in play now. So unbypass this, and let's actually increase our substeps to 15 since the simulation is really starting to get heavy now. And I'm going to go into the advanced tab, and here under fluids we have a parameter newly introduced in Houdini 19 called special sort interval. I'm going to turn this on. So special sorting is a new way of calculating the motion of neighboring points by making sure that the points that are near each other in 3D space are also near each other in memory. And it does this every 20 frames by default, so turning this on means more consistent and accurate results, but it also means faster sim time. I actually go over this more in depth in my Houdini Hive video, so check this out if you're interested. But basically turning this on makes your sims faster and your loose points fewer. And actually, before I cache this, let's go to our grains real quick. And I'm going to increase our resolution even more, so let's say 0.005. And I guess this is more than enough, and we'll call this our final resolution for the grain. So I'm going to cache this out now, and maybe we'll do one more adjustment before wrapping up this lesson. Alright, so before we actually can take a look at what we have now, let's focus on our split node for a second. We still have our bag coming from the left output, but now from the right output we don't only have the grains, but the cloth too, and our wires as well. So let's drop down another split node here, choose the stream grains, so it comes down from the left output, and let's copy this null over, name it cloth 2, and let's actually do another split here and split our group, our wires, and invert selection, so we have a cloth coming out of the left output, and from the right output we have our wires. Maybe drop down a polywire node, and if we type here at p-scale, this is the attribute controlled by the thickness. So if you remember, we made our thickness 0.02 for the string. So now we have this at 0.02. Let's merge everything together and take a look. Okay, and maybe let's divide this by 4. Alright, this makes more sense now. Alright, let's have a different color for our wires, like yellow color or something. And let's actually make a flipbook of this now so we can see what we have. Alright, we're very close now to what I wanted when I first started this project. One more thing I want to adjust is the break threshold of our bag. Let's see if we can't get it to hold on for a bit longer before it breaks apart. So let's go to our Weld Constraints and let's take this up from 0.25 to 0.4. And before cashing this out, I want to talk about something called integration. So let's jump into our .NET real quick. So right here in the Advanced tab, the first option that we get is integration, and we have an option called second order and an option called first order. And second order integration is the default, and it's more physically accurate than first order integration when it comes to retaining the object's energy, especially in non-linear motion, and it does a great job of predicting where the object will be in the next frame. But it kind of fails when it comes to calculating how much should an object bounce, and it could produce artifacts. So technically the first order integration is quote-unquote the cheaper option, but practically I often find first order result to be more realistic looking in most cases, especially when we have high constraint iterations like we do now, and it rarely causes any artifacts as well. So Vellum compensates for this integration differences by defaulting to the second order since it's the more mathematically accurate. But on detection collision, so if we go to the motion tab, we will find that on collision detection, it actually falls back to first order integration. So if Vellum detects any collision that is going to produce an acceleration that equals to or higher than 30, it defaults to the first order integration. And there's actually a great presentation by John Lynch about this that I highly recommend you to watch. But giving this information, we have two ways of experimenting with the integration orders here. Number one, we can set this threshold to a lower value, so Vellum doesn't have to wait for a collision that produces a max acceleration of 30 to happen to fall back to first order integration. So let's say we take this down to 5. Or we can actually sim the whole thing entirely in first order integration. So I'm going to try both, but first let's try taking down our max acceleration. Let's cache this out now, and let's see what kind of change does this give us in terms of behavior. Alright, so this is the result of the second order integration with the max acceleration turned down to 5. And while it's not bad by any means, it might be a little bit stable for my taste, as in the motion is more stable than I would have liked. I would have liked to see more bounce in the grains, more than this anyway. So let's try to cache with the first order integration now and see what we get. But before doing this, there is actually one last parameter that I need to talk about. So let's jump in our .NET. So in the common tab of our solver, in the friction options, we have this parameter that's called static threshold. So if our tangential velocity is less than this threshold right here, it will be completely eliminated through friction. In other words, raising this up might give us less sliding, and it's actually worth your time to play with this since friction can be one of those forces that you don't notice too much, but can increase the realism of your work if it's calculated properly. So I'll try to raise this to 2, and let's go to the Advanced tab. Turn our integration to first order, and I will revert this max acceleration parameter to its default. And let's cache this out now and see if our results are going to be better than the last time. Okay, I'm very happy with this now. The amount of time spent in anticipation before the bag tears apart makes the eventual tearing much more impactful, and we now have much more dynamic sand movement as well. And having this second layer of cloth tear apart as well makes this whole thing much more stimulating to watch. So this is the end of our time together. Thank you so much for watching and listening to me ramble about Vellum. I hope you've learned at least one new thing from this. and please let me know if you have any questions, and I'll see you guys in the next tutorial.